then the implementation of such multiplication may result in hundreds lines of highly optimized assembly code. And since humans make mistakes, what if such assembly implementation is wrong? Okay, then your crypto system may be broken and reveal your private messages. So we need to verify if the implementation is correct. For verification, it means we want to check if an implementation satisfies its specification. And for us, we focus on assembly implementation, and also we focus on functional specification. So let's first review some previous work on verifying crypto programs. The first approach uses theorem provers to manually prove specific implementations. And like in Coq, you may define a program semantics in Coq and manually construct a proof of the specification. Then when you after QED, the theorem prover Coq can certify your proof, or your proof is correct or not. And using a theorem prover allow you to prove some harder properties, but you have to construct a proof manually. And also, your proof usually is hard to be applied to prove other implementation. The second approach uses SMT solvers. So it translates verification problem to SMT formulas and then solve the formulas by SMT solvers. For SMT, it means satisfiability modular series, and a formula in SMT may look like this one. So you have expressions involving integer theory. You have expression involving data structure theory, like this is a linked list. And you may also have expressions involving bit vector theories. And these expressions may share some variables like A in integer theory and this A in data structure theory. And okay, so this approach uses SMT solvers. So SMT solvers is automatic. So you can solve formulas in this form automatically. But for some harder verification problems, usually SMT solvers cannot solve the problem. So sometimes you still need some human constructed lemmas to help the SMT solvers. And the one advantage of SMT solvers is that it can find bugs automatically. The third approach verify implementations via translation to polynomial entailments. So this GFVerif can verify some C implementations of curve 2519 and via translation to polynomial entailment. And this approach is fully automatic and it can prove correctness of algebraic properties, but it cannot find bugs. And also it still needs some overflow check to see if the program overflow or not. And in GFVerif, it implements a specialized range analysis to do it. Okay, so this is an example of polynomial entailment. You have some polynomial equations, whether this implies this one. So now our approach, we developed a sound decision procedure which performs overflow check with SMT solvers because it's automatic and there are very many mature SMT solvers. And we verified algebraic specifications with transformations to polynomial entailment. And the most important thing is that all our decision procedure is certified by Coq, except the results from the SMT solvers. So everything is certified and proved. And to make this easier, we proposed a domain-specific language called PV Cryptoline for modeling low-level mathematical construct in cryptography programs. And with our approach, well, we verified arithmetic computation over a finite field of order 2 to the power of 255 minus 19. And we also verify the Montgomery Ladderstep automatically. So now this is the syntax of our domain-specific language. We assume a word size W, which may be 64 or 32, depends on your architecture. And this VW is a set of all bit vectors of width W. Then we have variables X, Y, Z, and we have atomics, maybe a variable or constant. And we have some assembly instructions, like these are common in assembly. So we have addition with carry and set the carry flag, and subtraction, multiplication, for multiplication, left shifting, and two special command called split and concat shift. So for split, it means that we split a bit vector A at position 51, and then assign the high part to VH, assign the low part to VL. So this is split. For concat shift, we concat to a bit vector A1 and A2, then shift 13 bits from A2 to A1. So we assign this part to VH and assign this part to VL. So this is concat shifting. And then what kind of specification we can write for this PV cryptography program? We have two kinds of predicates, algebraic predicates and range predicates. This range algebraic predicates are evaluated over integers domain. And we can reason about equality or whether two numbers are equal modulo some number. And for range predicates, this is evaluated over the bit vector domain. And we have standard predicates like smaller or smaller than or equal. Then with these predicates, we can write specifications about PV cryptography and in this form. So we have a precondition containing an algebraic predicate, a range predicate, a program, and a postcondition. So this specification is valid if this statement is true. So it says if the program starts with memory state satisfying the precondition and terminates at some final state, then the final state will satisfy the postcondition. Okay. So now we have a program and give its specification as precondition and postcondition. How can we check this is true with our approach? So this is an overview of our approach. Starting with the specification, we first transform it into a static single assignment form where a variable is assigned at most once. Then by our theorem, we can reduce the validity of this specification into three parts. The first one is the validity of the range specification. So here, only range predicates involved. The second one is that whether this program is safe or not, which means it will not overflow. Then the third one is algebraic specification, but over integer domain. So I have a prefix Z, means that these are executed over integer domain. Then for the range specification and the safety of the program, we can translate the two problems to SMT formulas and then solve by SMT solvers. Then for the algebraic specification, we translate this problem to polynomial entailment. And then we use algebra systems such as singular magma to solve this polynomial entailment. And the results of this from the singular will feed back to our theorem prover Coq and certify whether the results from singular is correct or not. So everything in this green box is certified. I forgot this one. So now let me show you some details of our approach with a simple example. This multiplication, 100 lines of assembly code. No, I assume that most of variables are zero. So make the implementation easier. So it's just 4-line instructions and with some specification. Okay. So in our approach, first step, I will translate this specification into static single assignment form. Yeah. And our approach is standard. We just add index to variables. And every time a variable is assigned, we increase index by 1. For example, this here, we read R0 with index 1, and it is assigned here, so we increase index by 1, so it's now index by 2. And then we read R0 with index 2, and when it is updated, we increase the index by 1. So this is standard. Then, how do we translate the range specification to SMT formulas? Well, since our instructions involve mostly only bit vector operations, and in SMT's formulas, there are corresponding bit vector constructors. So this translation is very naive, one by one direction. And so I will just skip this one. Then the second one is prove that the program is safe, or it will never overflow. So we verify this by verifying a safety condition. Here, this safety condition says under the precondition, the program will not overflow. But what is the program does not overflow in the SMT formula? So let's look at this first instruction. This is a full multiplication. It will never overflow. But for the second one, concat shift, we shift certain bits from the lower bit vector to the higher bit vector, and this part will be discarded. So in order for a program not to overflow, we require that this discarded part must be 0. So here, the RDX1 should be smaller than 2 to the power of 51. So it will contain only values here. And then we also require that it will not shift too many bits. So should be smaller than the word size 64. Then for this multiplication, it will not overflow if the the higher 64 bits of the full multiplication is 0. So it is represented by this formula. Okay. The full multiplication and the high part should be 0. Then this again, this expression only involves bit vector operations, and it can be easily translated to SMT formulas. So now, how do we translate specification, algebraic specification over integer domain to polynomial entailments? For my presentation, I will skip the intermediate integer specification, just show you a direct translation from algebraic specification over bit vectors to polynomial entailments. So this is the SSF form we have. Now we want to convert it to a polynomial entailment. And then first we discard the range predicates and obtain this one. And then for the first instruction, it means that the result is this is high part RDS, and this RX hold the low results of the full multiplication. So this instruction can be represented by a polynomial equality. Says that RDX multiplied 2 to the power of 64 plus the lower part is the result of the multiplication. Then for concat shifting, we put the higher part to R01 and put the lower part to the R41. So the result of this concatenation should be equal to R01 multiplied 2 to the power of 51 plus the lower part R41. So this instruction is captured by this polynomial equation. But this is an over approximation because this equation does not require that R41, the value of R41 is smaller than 2 to the 51. So this holds even R41 contains values more than 2 to the 51. And then for the multiplication, we just use equal. And then for splitting, it's easier. So we have the higher part multiplied 2 to the 51 plus the lower part is the result of this Bay vector to be splitted. So we get this polynomial equation. Now, for the post condition, it's equality modulo some prime number. And for this one, we have A equals B modulo C. This is equivalent to exists some K such that A minus B is KC. So we rewrite this post condition to this form, and we get this one. So now everything is in polynomial, except that there is existential quantification. And we can take conjunctions of these polynomials equations and get this one polynomial entailment. And then actually, we can move the right-hand side expression to the left-hand side, and we get this one. So something equals 0 and something equals 0 implies, in this case, something equals k multiply something. So we end up with this polynomial entailment, and if this is true, then the original algebra specification is valid. So the next is how we solve polynomial entailments in this form. Okay, and we can solve this polynomial entailment in this form with algebra systems, but not directly. They cannot solve polynomial entailment directly. Unfortunately, by a work by John Harrison, this polynomial entailment holds if the Q is in the idea of E1, E2, En, and P. And the idea is a concept in mathematics. By the definition of ideal, Q is in the idea of this set of polynomials implies that Q can be rewritten as a linear combination of E1, E2, En, and P with coefficient C1, C2, Cn, and C. Then, from the premises, we know that E1 is 0, E2 is 0, so all these are 0. And then Q is exactly Cp. And then we find the weakness of K, which is C. So for this, to check if Q is in the ideal, singular can check this directly. And then we apply some approaches to find the weakness C, and then give Koch the weakness, and let Koch to certify that whether this weakness is correct or not. And then this to check whether Q is in the idea of the set of polynomials, the complexity is related to the number of variables polynomials in this set. So to make our verification faster, we apply some heuristic to reduce the number of polynomials here. So this is a polynomial entailment. You can rewrite this equation. You move this RDX to the right-hand side, and you get IS1 equals some expression. Then you can actually replace IS1 by the right-hand side expression. So the we eliminated one equation, and so on and so forth. We can remove more equations by rewriting, and this will make our approach much, much faster. So for experiment, we verify some arithmetic operations over 2 to the power of 255 minus 19, And let's see the hardest one, multiplication. It contains 144 lines of code, and it takes 4 seconds to check if the program is safe. And it takes 41 seconds to verify the range predicates. And without heuristic, it cannot verify the algebraic specification. And without heuristic, it can verify algebraic specification in roughly 2 seconds. And then plus the time to certify our the answers from singular, it total we need 82 seconds to verify multiplication. Compared to our previous work, which used SMT solvers to verify multiplication, our previous work needs more than 5,000 minutes to do it. But now it's just 82 seconds, and also our approach is certified. And besides the arithmetic operations, we also verify the ladder step. This is the specification of the ladder step. We verify after the ladder step, this four equation must hold. And then this is taken from the original paper. And it takes around 5.5 days to verify the ladder step automatically. And then if we run the four, if we verify the four equations separated in parallel, then actually we only need 2 days. So for future work, currently we verify programs in PV Crypto9, and then we may need automatic translation from other assembly language to our domain-specific languages. And again, also currently everything is certified except the SMT solvers. So it would be good if we have certified range analysis. And also our work is sound but not complete. We can prove the correctness, but we cannot find bugs. So we would like to integrate with bug finding approaches. And then we want to apply our approach to verify more industrial crypto programs. Thank you. Yes, we are trying to verifying assembly code in OpenSSL. We actually build a translator, but not certified translator from assembly code to our domain-specific language and to verify it. Because our approach is not complete, so we cannot find bugs. So yeah.
Hi, thanks. Can you say anything about what kind of programs would be um, harder or easier to use with this approach? Like the algebraic methods, I guess, would scale badly with the degree or something, and so some kinds of if there was a lot of chains of multiplications, I don't know. Can you say anything about that? What kind of programs would scale better for this approach?
Okay. So for some implementations, you may need to add some preconditions that cannot be eliminated by our rewriting. Then we will have uh, well, we will have to prove that whether something is in the idea of many polynomials. Then this will take a lot of time. And the other case is that the programs may need some hidden information to prove the correctness, which is not in the condition and in the box condition. Then sometimes we need to assert that something in the middle is true. And yeah, it may still happen.
Could you do me a favor and say your name and say your topic one more time?
Okay, my name is Ming-Hsien Tsai, and our talk is certified certified verification of algebra properties on low-level assembly.